All right, welcome back. We'll be talking about two-way slabs today. Again, ACI 318 and all other many structural codes for that matter are very heavy on text but light on visuals. My goal is to take these dense, complex clauses and bridge the gap with simple hand-drawn sketches. I'll be drawing. You'll see me drawing some chicken scratch that they don't look pretty good, but then idea is to layer these chicken scratches directly onto the code canvas. I'm trying to transform abstract rules into clear mental images. This visual association makes it much easier for you to recall specific requirements when you are under pressure in an exam setting. In this video, we'll be breaking down chapter 10, which is two-way slabs. We'll be talking about, we'll not cover, chapter 10 is pretty big. We'll not cover everything. Sorry, chapter 8 my bad. Chapter we'll be talking about chapter 8, which is two-way slabs. We are ACI 318. Chapter is pretty big, but then we'll be talking about um, we'll keep the breadth, SE breadth, and PE exam type questions in mind, and we'll be touching upon only important concepts. For example, there's something called equivalent frame method, and if you get into those weeds, I don't think you can expect a problem that needs a computer to solve, right? So we'll be talking about problems that will be in the exam. It's my guess. I'm not trying to. I don't know anything about um, how the board comes up with these questions, but um, we'll be talking about a simpler concept. In short, I'll not be touching about every little detail, but then we'll be going through some basic details. Okay, so let's jump to chapter 8. I think it is page 95, maybe. Yep, chapter 95. Uh, now this is for a two-way slab. We're talking about a two-way slab. And when it comes to two-way slab, that means we are talking about a slab which is something which resembles, which is close to a square, or it's not something like this, right? Wherein the aspect ratio L1 by L2 in this case is way greater than 2. Whereas here this is L2, L1, this is less than 2. So we're talking about slabs like this, wherein the distribution of the load will happen in two ways. Whereas here the distribution, if you just provide reinforcement in this direction, you are good, right? Whereas here you have to provide reinforcement in this direction and also design reinforcement in that direction. Okay, so that's what we will do. We will talk about some basic terminology here. They should have given a visual. So for example, there's something called a drop panel. What that means, before drop panel, let's talk about what a flat um, slab, a flat plate is. Because um, in the exam there might be a question related to, okay, what is the minimum thickness of this particular span of a flat plate, right? So you need to understand what a flat plate is. Unfortunately, there's no picture here. So flat plate is something like a slab, right? And there are columns like that. That's about it, right? There's no beams in between or anything like that. So this is a flat. This is an example of a flat plate. Um, Whereas a flat slab can have, so now we are talking about flat slab, right? A flat slab is a flat plate with the drop panels. For example, so let's draw this flat plate, and there is a drop panel like that, and here is your column, right? There's a drop panel, there's like that, right? So the next column might be, next drop panel can start from here. Here is your next column, that's the drop panel. So this is called a flat slab, and this portion here is called the drop panel, right? So whenever there's a drop panel, there are certain dimensions that need to be respected. Otherwise, you cannot call a 2-inch section which has been dropped as a drop panel. So this part of the code says if you have a drop panel, you will have to find out what this length is. Let's say the length is L between these two, between the next column, right? And then the drop panel should be at least greater than or equal to the length of the drop panel, which is from here to here, should be greater than or equal to L1 by 6. So that is one requirement. The other requirement is about the drop. How much should this drop be? So to call this a drop panel, that drop should be equal to quarter of the thickness of this adjacent slab. So let's say the thickness of the slab is h, then this is quarter. So we talked about this dimension here, and we talked about that thickness here. Okay, and we talked about drop panel. So this is a slab with a drop panel. So now let's talk about something called shear cap, right? So we talked about this section. Now we are talking about that section. Shear cap. A shear cap means you have a slab, and then instead of a column like that, what you're going to do is you're going to locally thicken near the column, right? And go like that, right? So this is called now that section. This is a shear cap. Okay. Now why do we do that? That's a slightly deeper topic, but then the idea is if you have a slab like that with your column like this, right? Um, and there is load on the top, so the load is trying to push the slab down through the column, right? And what happens is the slab will start to crack in that direction at an angle 45 degrees, meaning there's something called a critical plane, which is at d by 2 from the face. D by 2. Let's say this is d, then d by 2 from the face of the column. You have your critical section 1 1, critical section 1 1. Okay. So in plan view, let's say here is the slab, and that is your column, right? This column edge lines up with that edge. The critical section might be that much, and and let us say that the load is acting on this area. This is the tributary area, and the entire area, so let's say that is A, and times your QU is the factored load acting on it. That is the shear force, and the force is resisted by this area here, right? This is the perimeter. So let's say B, 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 and B. So add all those four, and you get a perimeter. How do you get the B dimension again? The B dimension is nothing but the width of the column plus D by 2. Right? So if this is the width of the column, and I'm drawing the perimeter here, right? Let's talk about a square column. So let's say the column is C1. Okay, the width of the column is C1. C1 plus D by 2 is this dimension. C1 plus C1 plus D by 2 is this dimension. So you add that entire thing, then you get a perimeter. The perimeter is usually dictated by the code by V naught. Okay, so B naught times the thickness normal to the screen is the area resisting this particular force, right? So in short, I mean, if to improve the shear capacity, you want to increase this perimeter, right? That means you want to push your critical shear plane outside from, and currently it is the shear plane is here. You want to push the shear plane outside. Okay, so how do you push that? What you do is you introduce a local thickness. You thicken the slab locally. That means you introduce a shear cap, and by doing a shear cap, the plane is no more. It's not here, but you push this plane which was here earlier to this location there, right? So now now your critical location 2 and 2 is that, right? Yes, there is a shear plane here, but then the depth is so much that you increase your area drastically. So whereas by pushing it here into this slab, the slab is only, let's say the thickness of the slab is D2, then the distance of that critical plane, which is this one, this critical plane from this edge, right? That distance is D2 by 2. D2 is the thickness of the adjacent slab. So in plan view, that means we have, I mean, now the shear cap is somewhere here, right? um, I mean, shear cap is there. The section D2, sorry, section 2 critical section is somewhere here. That means this section is much bigger than the earlier perimeter B naught. So let's say this one, the perimeter of this one is B naught hat, right? B naught dash. The B naught dash is much greater than your B naught. Right? So you improve the shear strength by just adding a local shear cap. Okay, so that's what shear cap is about. Let's see what this section reads. A shear cap, when used to increase the critical strength um, for, um, for shear at a slab joint, shall project below the soffit and extend horizontally from the face of the column a distance at least equal to the thickness of projection below the projection below the soffit. So you cannot say that, okay, here is my, I'll just do like that and call that a shear cap. You cannot do that, right? So the depth of that shear cap, for example, the depth of that shear cap should at least be equal to the, if this is the depth of the slab, this should be at least be equal to thickness of the projection below, so at least equal to thickness of the projection below the soffit, at least equal to that much. Okay. So from the face of the column, the shear cap were used to increase the critical section for shear at a slab column joint shall project below the slab soffit. That means shall project below this point um, and extend horizontally from the face of the column a distance at least equal to the thickness of the projection below the soffit. Oh, so it has to extend. Um, all right. So just to be clear, this section here, we're talking about shear cap, right? Slab, locally thicken it. Here is your column, locally thicken it, right? So this dimension from here to there, that should be comparable to that dimension. If that dimension is D2, then this has to be greater than or equal to D2. So that is what this section is talking about. Okay, let's move on. We talked about shear cap. This is a pretty important section. Again, very light on pictures, but then pretty heavy in terms of visualizing. That makes it very heavy on visualization. Okay. So firstly, this is about calculating the minimum thickness of a two-way slab, which does not have without interior beams between support. Okay. Now, this section here, that section here is for flat slab, whereas this section here is for flat. Sorry, I think I got it backwards. This is for flat plate. This is for flat slab. Because remember, flat plate is something without a drop panel. So for example, again, the flat plate will look something like that. So this is one column, there's another column, maybe there's a column on top, right? So that is a flat plate. Whereas a flat slab will look like something with a with either a drop panel or a shear cap. So with a drop panel. Okay. So if you have to decide the minimum thickness of a flat plate, then you come to this box, right? And then decide if you are in the exterior panel, if you are deciding the thickness of the exterior panel, or if you are deciding the thickness of interior panel. Whereas if you are talking about if you are deciding the thickness of a flat slab, then you come to this section, and then you need to decide if you are deciding the thickness of exterior panel or interior panel. Okay. But um, even after you decide if it is an exterior panel, let's say you decide it is an exterior panel, there are two options again. Does your exterior panel have an edge beam, or it does not have an edge beam? Okay. So what is an edge beam? Again, this, let's say this is the end span, so there might be a beam like that here, and it is usually to let's say you want to hang a curtain wall or a glass shade system or something like that. You want to anchor it to the beam, correct? Um, so this is a, and let us say you want to decide the thickness of this span. So this is a span which is an exterior span. Sorry, this is a slab for which you there is a edge beam, correct? And if that edge beam has some character, meaning the relative stiffness of the edge beam to the compared to the stiffness of the slab. If that is above a certain value, we'll talk about all that. But then if that is above a certain value, you consider that your edge beam is active, and you pick up based on your Fy value. You pick up the thickness as ln by, for example, let's say you have a say Fy 60,000 psi interior sorry edge panel. um, let's do this again. So let's say you have 60,000 Fy and you have the edge beam. Your edge beam here is active, right? You decided that it has decent meat on it, right? Then you come here and you pick up your thickness ln. What is ln? Ln would be from uh, that span. Ln will be clear span, right? That means ln would be, let's say this is the edge beam. That's a flat slab, right? Like that. Ln would be, if you look at here, clear span, neat. That's how I remember, but ln, neat surface from here to here. So that's the ln. Okay. So if you have an edge beam, then you again, and you are an exterior panel, so you get here, and then you, based on the Fy, you pick up your thickness value. If you don't have an edge beam and you are in an exterior panel, you pick up your thickness from there. Okay. But then just by providing, let us say I have an edge beam like this, right? And here is my column, this is another column, and this is my slab. Okay, very thin edge beam, and the beam doesn't have any character to it, right? So you have to judge if this beam um, passes a certain requirement, and that requirement is here. So you have to calculate something called an alpha f value for that edge beam, and if that alpha f value is less than 0.8, which is here, that means your edge beam doesn't have any character to it, and you have to ignore the edge beam, and you pick up your thickness. Let us say you are here, you pick up your thickness from the column which says without an edge beam. Okay. But if your alpha f value of that edge beam is greater than 0.8, that means the edge beam has a decent meat on it, and then you pick up your value from this column here, wherein it says with edge beam, meaning you consider your edge beam as present and active, right? So how do you find the alpha value? The alpha f, again, the formula is there, but in short, it is the relative stiffness. Relative meaning it relates to the stiffness of the beam to the stiffness of the slab. And let's say you have Young's modulus of the concrete of the beam, Young's modulus of concrete of the slab. So EC, IB, ES, IS is your alpha B value. Okay. um, it will appear simple, but it's not that straightforward to calculate your IB. Um, so let's say you have a span like that, and you have an integrally built beam like this here, right? IB is not just just the moment of inertia of this beam. The code says you have to go 45 degrees like that, go 45 degrees like that, and consider the portion of the slab within that region as part of your beam. Okay, and you calculate the IB of that hatched section and not the IB of just your beam itself. We'll talk about it. I'll show you that requirement here shortly, but because we are here, I thought I will talk about it. um, but there is also a limitation. There is also a maximum limit to that dimension. I think that limit is like 4 times HEF, 4 times H of this slab. So H, let's say HF is that thickness of that slab. Then that should be less than whatever you calculate. When you project it like that, it should be less than that 4 times of HEF. Okay. Again, how do you do that? Here is a slab. This is, let's say this is your beam cast integrally with the slab. The EC beam, I beam by EC slab, I slab is your alpha F, and that is what you want to calculate. Why do you want to calculate that? You want to see if your edge, if you fall in this column here or this column here, right? You might have an edge beam, but edge beam may not have character to it. So you have to find your alpha F of the edge beam, and then compare it with 0.8. And if the alpha F is less than 0.8, then you treat the edge beam as if it is not there. Okay. So to calculate the moment of inertia of the beam, you go 45 degrees like that, go 45 degrees like that. So that means if this depth is h1 plus h2, then this is h1 plus h2, right? So that width is h1 plus h2 because 45 degrees. But that should be, there is an upper limit to that width. It should be less than or equal to 4 times of your h1. Okay. So you go there, follow that rule, and pick up your portion of slab and consider that as a beam, and then calculate the moment of inertia of this. Right, that gives you this value. This is a straightforward, depending upon the concrete that is used to build the slab. Right. Now let's talk about the slab portion. Right. So let's say you have here is the slab. Now again the beam is integrally built. Right, and maybe there is a there is a column here. Next beam is there, whatever. Correct. So the moment of inertia would be maybe the same thing. Maybe there is a column there. The moment of inertia would be of the slab would be from the center line of that span to the center line of this span. So this portion, this entire portion of the slab has to be considered in the moment of inertia of the slab calculation. Okay. So that is for the moment of inertia of the slab, and you need to consider this portion for your moment of inertia of beam calculation. This is for your I beam. Okay, you have I beam, you have IS, then E Young's modulus of beam, I beam by Young's modulus of concrete, I slab, sorry, slab, I slab. You calculate your alpha F value. Find the alpha F value. If it is less than 0.8, then that means there is no edge beam. You fall in this box. If it is greater than 0.8, then you fall in this box. And based on the Fi of your steel, pick up your thickness. Okay, and that is for flat plate. Now we get into flat slab. Flat slab is something which might have a drop panel, right? Again, the same thing. If it's an exterior panel, interior panel, if you have edge beam or you don't have an edge beam, or you have an edge beam but it doesn't have character, that means you don't have an edge beam, right? And then you come based on your Fi value, you come and pick up your thickness. Okay, that is all there is. This is what the code says, but then you can also run your finite element analysis to find out your thickness. If that thickness can be less than this thickness, it is allowed, but provided the deflection is under control. Okay, and it should also meet the deflection from your analysis should also meet that criteria there. Okay, so that's about this one. And this is for again minimum thickness. We are still in the minimum thickness. This entire section is to decide minimum thickness of a slab. But then this portion here, table 8.3.1.2, is minimum thickness of a non-prestressed two-way slab with beams spanning on all sides. For example, that means you have a slab like that. Let's say you're looking at the slab from the bottom, right? So let's say that's a slab. Here is the thickness of the slab, and there are beams running underneath the slab like that, right? Let's say that's one column, there's another column, there's another column, there's another column. Okay, so that means you have a beam like that, beam here, beam here, beam here, beam 1, beam 2, beam 3, beam 4. Okay, maybe they are all of the same dimension, or maybe they are of a slightly different dimension. But then to decide your alpha F value, you have to take an average of the alpha F's of all those beams. That means alpha Fm is alpha F1 plus alpha F2 plus alpha F3 plus alpha F4 divided by 4, right? So you find the alpha F's of all those, and then see if you are in this range or on that range. Okay, let's say you are in this range here. Let's say you are in this region here. Then you find that and find this and pick up your value as a maximum value of between this and that. Okay, find this and find that and pick up your maximum value. And if you see this formula here, it also has the beta of the slab. That means the span ratio. You take let's say this is L1, L2 of that panel. You find out your beta as clear span long to the short. Let's say L1 is longer than L2, then your beta is L1 by L2. Okay, So you find your beta, right? You find your beta value there. So that is known. Then you have your alpha FM, so that is known. Then you find Fy 2000, all the other constants are given. Ln is again clear span, right? Um, then you can calculate your alpha FM, and from the alpha FM you decide your depending upon the range where it falls between these two numbers, or it is greater than 2, then you have to pick up your slab thickness from here. Okay, so in short, this is for beams without interior beams, this is for beams with interior beams. Okay, so that's what that table is. Okay, so we talked about thickness. Now let's talk about deflection is not super important, meaning you can, if questions are pretty may not be straightforward. This is another important topic which is called column strip. There is a picture somewhere there down, but then let us say you have a layout of your columns like this, and pointedly I will draw this column slightly far away. Let's say here is your slab, right? Slab like that. Okay. Um, yeah. So this, I mean, the portions of the slab which are near to the column will attract, are more rigid. So meaning they attract more load, and so that's why they have to be designed. So it is convenient to divide the entire slab as a column strip and middle strip. And code gives you guidelines as to how you can divide the slab to fix the dimensions of that column strip and middle strip. Okay, so let's say from the center line to center line, this span is L1, and let us assume that it is same on both the directions. So this is also L1, and the dimension perpendicular is L2. Okay, so and column strip is a strip which is on from the center line of those columns. It is on either side, on this side as well as on that side. Okay, so column strip is that hatched portion. Okay, but how wide is it? That depends upon your L1. You compare your L1 and L2 ratios, and you pick up your L value as a minimum of L1 and L2, right? And then then this dimension here from here to here, or let me write it from here to here, will be 0.25 times of that L value, and from here to here will be 0.25 times of L value. Okay, so that is how you decide the edge strip, and whatever is not the edge strip will become the middle strip. Okay, but then there might be a tricky question wherein you are given a layout like that, right? Um, So this is, let's say this one, let's say this one, let's say this one. You have another column, right? And then you have your slab like that, right? So let's say this is 10 feet. Let us say this is 12 feet, and let us say this is 14 feet, just for example. Right now, the column strip is not. So to decide the boundary of the column strip on this side, what you do, you compare at 12 and 14, pick up the minimum value and multiply. So minimum min of 12 and 14, right? 12, you multiply 12 by 0.25, and that is the distance from here to here, right? So in this case, it is 0.25 times of 12, because between 12 and 14, that's the minimum value. Now you come to the other side, then you have to look at this dimension 10 and 14, right? So compare 10. So minimum value between 10 and 14 is your L. So L is equal to 10. 10 times the dimension of the column strip is 0.25 times of that L, which is 0.25 times of 10. So that is the other next boundary. So the column strip is not symmetric, but then it is defined like that. Okay, so that's the important point. Yes, it's all described in words, but then um, not easy, super easy to visualize, right? When you have different dimensions in different directions. Okay, so that's about column strip and middle strip. This is what I was referring to earlier. If you have a beam like that, which is integrally built with the slab, a portion of the beam a portion of the slab should also be accounted as the beam when you compute your moment of inertia of the beam, right? And the way you do it, let's say BW, let us say this is HB, then you go 45 degrees, then that means this is BW from the center line BW by 2 plus HB, right? But that has to be less than this particular value. Okay. The same thing, let's say you're at an end span. Here is your beam. You can just not consider this as the beam. You have to consider a portion of the slab as your beam. The portion of the slab that you need to consider as beam is given by that particular rule. Again, you have to go here, find out the dimension. If that dimension is less than 4HF, then you take you consider that portion as part of your beam. Right now, if you have a beam like that, you have beam like that, and let us say that is the slab, right? You decide that this portion of your slab is participating in the beam, and you need to find out the moment of inertia. So your easiest thing is to split this as section 1, split this as area 2, use your parallel axis theorem, find out your y bar as a1 y1 bar plus a2 y2 bar by a1 plus a2, right? Y bar is from here. Let's say this is a reference from here to the half the depth of the beam. Y2 bar is from here, the same reference point to half of that, right? You find out that, and then you start using parallel axis theorem. Ixx of the shape 1 plus area of the shape 1 into h1 square plus Ixx of shape 2 plus area of shape 2 times of h2 square, where your h1 is y bar minus y1 and h2 is y bar minus y2. Okay, so that's how you calculate the moment of inertia of this particular shape using parallel axis theorem. Okay. So use the technique and find out your value. Once you find out your, again I'm repeating here, once you find your IB, ECB, Young's modulus of the beam, Young's modulus of slab, I slab, right? And you find your alpha F value. If the alpha F value is less than a certain value, then your edge beam is considered to be useless. If for thickness computation, if alpha F is greater than 0.8, then your edge beam is good. Okay, and you pick up the thickness accordingly. So factor moment, again, this is we'll skip this section here. We'll go to the next important topic is one-way and two-way shear. Mostly two-way shear is important in two-way slab. But factored one-way shear, how do you calculate it? Factor two-way shear, how do you calculate it? Factor so one-way shear, what is your critical section, and two-way shear, what is your critical section? That is all described here. But then if we have to do a quick visual, let us say our layout is something like this. Let us say there are 1, 2, 3. There's another column, another column, another column. Here is edge, edge, edge. So let's say that is your slab there. Okay. For two-way shear, let's talk about two-way shear and we come back to one-way shear. Two-way shear happens at a distance of d by 2 from the face of the column, meaning this perimeter, the shear perimeter that we talked about last time, that is from here to here, it is d by 2. So d by 2. D is the depth of your slab, right? Same thing here. From here to here, it is d by 2. So this is the perimeter that we are referring to when you're talking about a two-way slab. Okay, but the load comes from, let us say this is the center line of this panel, center line of that panel. Load on that particular column that we have highlighted will come from this portion here within this boundary, right? So the load will come from that boundary. You take the area of that boundary times you multiply it with your factored shear, that is your factored shear force. You divide that shear force with this particular area to calculate your factor shear stress, right? And you once you compare your stress, then you go to a certain chapter, I think somewhere here, and then find out the limits and see if the stress is within the limit. So that is for this particular column. Now for this column which is at the edge here, so the critical section might be something like that, correct? It's only on three sides, nothing on the other side. The critical section is that, and this will be your influence area, right? So that will be your influence area for that calculation. Again, the distance from the face to the critical section is d by 2, where d is your thickness of the slab. Same thing from here to here will be d by 2. So you have to manually calculate the length of this perimeter, multiply with the thickness of the slab to get the area of the area of the shear resisting area. So in that case, if you draw it in 3D, it might be something like this, right? So that is the area which is resisting your shear. Shear value is A times of QU. QU is the factor load in PSF or a KSF. A is the influence or tributary area times this. So this will be a force acting on this particular area. Force by area will get you your shear. You compare that with your strength and take a call, right? For a section which is somewhere here, let's say this is a column, this is an edge column, right? The column is right there. Now your perimeter will again be d by 2, d by 2, right? From here to here, d by 2. So that is your critical perimeter. The tributary area will be this area here, right? Area contributing to area within that line will be borne by the you ignore that area, but then area outside is what area within that line is will be borne directly by the column, but the area outside that critical perimeter is the area which is actually causing your shear. Okay. So we talked about two-way shear. If you have to do one-way shear is, let's say for this column here, you want to calculate the one-way shear. Then it is from a distance d. The critical surface is from a distance d, not d by 2, from the face of the column, and this entire area is the tributary. This entire area here is the tributary area contributing to that shear. So this is A2. You multiply it with the Q2, and um, um, the critical edge is that. So the critical edge will be something like that, right? You multiply these two, you get your force. You divide it by this area, you get your shear stress. Compare it with your shear strength and qualify the whole thing. Okay. So in short, one-way shear happening at a D from face of support, whereas this one is happening two-way shear is happening at a distance D by 2 from the face of the support. Where is that detail? I think we have to go to that that section there to really understand. Okay, so that's where this information is. Two-way shear critical section shall be located at perimeter B naught, which is at a distance D by 2 from the face of the support. Okay. Now, once you find your stresses, you have to compare them with the shear strength of concrete, right? Now, how do you find the shear strength of the concrete? So this is a small VC, not capital VC, small VC, VC, not VC. This is force, whereas this is stress. Okay, so the VC stress can be calculated as the least of these three. Again, lambda, lightweight concrete, lambda is equal to 1. You know FC prime for the only new term here is beta. Beta is nothing but it's given here ratio of the long side to the short side of the column, nothing to do with the slab, right? So you find out your beta, you calculate this one. In this term, there is your B naught, which is your perimeter of your, let's say this is the column, and let's say this is the critical shear plane. B naught is the sum of B1, B2, B3. If it is a rectangular column, all this may be different. B4. You sum them up to find out your B naught value. That is the perimeter, length of the perimeter, and use that perimeter here. And there is a alpha S. alpha S is defined below. It depends upon the placement of your column. If you're referring to an interior column, I think here alpha S. If you're talking about interior column, alpha S is equal to 40. The column which has three sides, then yeah, for an edge column, let's say you have a column like this, which is here. This is the edge of the slab. Then the alpha S value is equal to 30. Whereas if you have a column, column, bunch of columns, and you're talking about this column, right? For this alpha S, this is an interior column. Alpha S is equal to 40. Okay, so depending upon if you have a column, let us say at the very corner like that, then your alpha S is equal to 20. So alpha S 20, interior column alpha S is equal to 40, and edge column alpha S is equal to 30. So compute your alpha S, go back here, find out your, in this formula you need alpha S, you need the depth of the slab, you need beta naught, right? Sometimes this particular fraction is less than 2, and then this might control the entire thing, right? So if that is greater than 2, then maybe this will control the entire thing. Okay, so in short, this table here, we are calculating our VC value, which is the shear stress, right? So you compare the shear, this is the strength, not shear stress, this is the shear strength, right? So you take the shear strength, multiply it with your area that resists the shear, and multiply that with the free factor. That means this is the nominal strength, this is the factored strength, and you would expect this to be greater than your factored shear. If that happens, then your design is good. If that doesn't happen, then you have to revise it. Okay. So let's go back to chapter 8. Chapter 8. Okay, I think chapter 8 is page number 90. So let's say, I think we were in 102, somewhere there. Okay, so that's about this one. The last topic I want to talk about is this is pretty straightforward here, right? Your strength phi times the nominal moment should be greater than or equal to your factored moment. Phi times the nominal nominal shear should be greater than your factored shear. Same like beam design, column design. Okay, so that's pretty straightforward. Now let's talk about, let's not talk about reinforcement. We'll talk about another important topic, which is how do you decide your, okay, which is called, talk about that, which is called direct design, DDM, or direct design method, which is 810. 810 is, I don't have a document with, okay, so 810 is here. This is how you design your slab. Might be some questions from this section. A direct design method. It applies to apply direct design method. There are certain conditions. Those conditions are all listed. Direct design method, set of rules, determination of the total factor static moment. This is what you do with direct design method. It consists of set of rules for distributing your moments to the slab and beam sections to satisfy safety requirements, right? So you determine something called a static moment, which is m naught. We'll talk about it in detail, and then try to distribute that m naught into negative and positive components. And after you distribute that, then distribute that further, distribute the negative and positive components further into the middle strip and column strips. Okay, once you have the moment on the column strip, then you can design the column strip or middle strip, and then uh, for calculate the reinforcement and all that. Okay, so the limitations of the direct design method, it only applies if all these conditions are met. So this is the section, right? Successive span lengths, there is a rule on the successive span lengths. You can read that. Panel shall be rectangular with ratio of longer to the shorter panel not exceeding 2, right? The column offset, if you have to offset a column, then offset should be within 10%. All loads are due to the gravity and uniformly distributed loads, and they're on all the spans, right? It's not that two spans are loaded and the third span is not loaded, right? And then the last one, there's also another requirement. Your live load, unfactored live load, shall not exceed the dead load by what, two times. So that should not happen. Usually that will not, but that should not happen. Then you can apply your direct design method. Okay, now we talked about this. It should be familiar by now. We talked about this is how you calculate your alpha value, right? um, so in direct design method, one principle is, let's say you have a fixed beam like that, fixed beam subjected to UDL. Imagine this is your slab subjected to UDL W. Then we know that the negative moment, there will be a positive moment. This is positive, this is negative. The negative moment is what? WL square by 12. So this one here is also WL square by 12. The positive moment from here to here is WL square by 24, right? In other words, um, you take the fixed beam like that, negative, positive, you add up your WL square by 12, and you add up your WL square by 24, then you will get WL square by 8. So that means from here to here, that value is nothing but WL square by 8, right? This is like your simply supported beam subjected to UDL. Then your bending moment is WL square by 8. That value is WL square by 8. Okay, so um, so the static moment is called m naught, and that is computed. The static moment is from here to here, and that is computed as W. If you see, it is similar to WL square by 8. Okay, wherein the Q it currently it is QU L2 Ln square by 8. So if you treat this component as your W, then this is nothing but W, and this is whole thing is equal to your static moment m naught. Okay, so QU times L2 times Ln. So let's talk about this. How is that QU times L2 your UDL? Okay, so now call bunch of columns like that. Here is your slab, right? This span Ln is what? Clear span. So from here to here, this is the span in the long direction in which you want to calculate your moment, static moment. So that is Ln. Okay, so from here to here is Ln, and let us say from here to here, this is your L2. Okay, this is L2. Okay, then you take your QU, which is a factored floor load. You take that, which is in PSF or KSF. You take that, multiply that with your L2, which is from here to here, right? You multiply it with half L2 on this side, half L2 on this side. So you're multiplying effectively with L2. That means you're talking about a UDL in this direction. Okay, you multiply width in this direction, you get UDL in the other direction. So you have a beam. So this is L. This span from here to here is Ln, right? And this fellow, you rotate the picture like that. That means you have a simply supported beam. W is QU times L2, and the span is L. So that's your UDL. That means your moment is WL square by 8, which is QU L2 is UDL times Ln square by 8. So that is your static moment, and that is the static moment that we are referring to here. Okay. So the idea is to take the static moment and depending upon if you're looking at interior panel or exterior panel, you distribute the static moment um, yeah, into a negative and positive zone, right? And then use that moment further distributed it onto a column strip and then find out your reinforcement needed for column strip and all that. So this is the most important table. There's a lot here. I mean, it looks pretty simple, but then um, we will have to really look into a bunch of um, scenarios here. Right, let's go up a little bit. If you see here, um, this is about distribution of that m naught, that static moment, that m naught. How do you distribute it? If you are looking at an interior span, again, interior span is let's say you have a slab like that, right? You have a column here, slab continues is a column here, column there, right? And maybe this is sitting on a beam like that. So interior span is this span. Okay, so interior span is as good as a fixed beam, right? So this can be idealized as a fixed beam. So that's why the code says you take your m naught, and um, 0.65 times of m naught you distribute it to the negative region, and 0.35 times of n naught you distribute it to the positive region. So this value here from here to here, that is 0.65 times of m naught, whereas the positive is 0.35 times of m naught, right? So you take m naught. Finally, what we are doing is we calculated m naught. How did we calculate m naught again? M naught we calculated as QU times of L2, that is my UDL, times my span square by 8. That was my m naught. I'm taking that m naught value and I'm trying to distribute it to the negative region and the positive region. On the negative region, I do 0.65 times m naught, and positive region 0.35 times of m naught. Okay, and that applies only for the interior. This whole thing is only for your interior span. Okay, but if you're trying to do the same thing for the exterior span, then there are a bunch of scenarios that you need to consider, and you need to consider this table here. Okay, so let's talk about, as the last thing, let's talk about the table, and we should be good. For example, here is the table, right? And if you see this, the, firstly, are you talking about? I mean, when you have a table, you need to see if you fall in this row, this column, or this row, that column, like that, right? So let's talk about this column here. Okay, exterior edge unrestrained. That means this is a scenario wherein you have your slab. I'll just draw a couple of spans. Let's say that's your slab. This is your column. That's your column, right? This is the interior span. We are not talking about this. We're talking about the exterior span, and the exterior span is just resting on a beam like that, right? Simple support. So when that happens, your exterior edge is unrestrained, meaning if I apply a load like that, that slab can lift up like that, right? So when that happens, exterior negative, exterior is this side, negative is 0, so your bending moment here is 0. Positive is 0.63, so here positive span 0.63 of your m naught, and interior negative, that means here it is 0.75 times of m naught. So like that, right? So positive 0.63 from here, negative 0.775 from here. Okay, so now again, this only covers this particular column here. There's no picture in the code, but then that's how it has to be interpreted. Okay, so mainly most important thing is your exterior span is just resting unrestrained and just resting on a column there. Okay, that is when this particular column applies. Okay, now let's talk about this one. So this one here is slabs with beams between all supports. Okay, then we'll talk about without beams, and then we'll talk about something else. So this is when you have a slab you have a slab like that, right? Let's say there's a column, you have slab, column, and a column. Maybe let's there is a column here, right? Here, right? And then there is a beam also built in. So this is the beam portion which is built in with the slab. Okay, so there are interior beams. So everywhere there is an interior beam between your supports, right? So when that happens, again, the focus of this table is only for your exterior span. So we are not talking about this span, because at this span, pretty easy. This span business is very easy, because you just consider that as a fixed, correct? And then take your static moment. It will be like that, right? So here it is WL square by 24, and sorry, you take your m naught, and 0.35 times of m naught is a positive, and 0.65 times 0.65 times of m naught is the negative. Okay, but the focus of this table, like I said, and this column here applies to the exterior spans, this fellow and this fellow. So you have an exterior span. Interior negative is that region, interior negative is this region. So here it is 0.7 times of m naught. Interior positive is 0.57. Here it is 0.57 times m naught, right? Exterior negative is 0.6, 0.16, that and that. So that's how you are bending. This is the negative, this is the positive, this is the negative region. That's how you define your bending moments. Okay. Now the same thing, but if you now let's talk about this particular column here. So that is for slabs without beams between interior supports. So meaning maybe you have a column like that, beam column like that, right? And this fellow, that's your thing. And then maybe there is an edge beam here, right? Um, So if you have an edge beam and you're talking about that span, then you're talking about it. Again, this is the exterior span. We are not talking about the interior span, because interior span is pretty straightforward. Edge beam is that edge beam. You have an edge beam. Sorry, you don't have an edge beam. Uh, if you don't have an edge beam, then your interior negative, positive, and exterior negative. If you have an edge beam, that then your interior negative will be here 0.7 times of m naught, positive will be there 0.5 times of 0.5 times of m naught, and exterior negative, sorry, exterior negative is this side here. Okay, let me draw this again. You have an edge beam, slab, column, slab, like that, right? Maybe this is built in like that. Okay, so that's the condition. We have an edge beam. So with edge beam, we are talking about this scenario. Interior negative is somewhere here, 0.7 m naught. This one positive happens mid-span, somewhere close to mid-span, maybe like there. And this one exterior negative, 0.3. So 0.3, that's your bending moment diagram. That's how you distribute your m naught. You take your m naught and distribute it like this: 0.5 m naught, 0.3 m naught, 0.00 m naught. Okay. Again, okay. So this last column here, this column is straightforward without an edge beam, right? You have an exterior span without an edge beam, and there are no beams between the supports. Then you fall under that criteria. Then you calculate interior, positive, and exterior. The last one is a case wherein, let's say you have a column like that, column like this, and then it is built into, that's your slab, column, column, let's say. Okay. And if you see this, this is built in, maybe you're continuing the reinforcement from the slab into the column, and it is all fully restrained. I mean, the stiffness of the column here is 8 times the stiffness of the, equal to or greater than 8 times the stiffness of the slab. Then that's when you consider this as an exterior fully restrained. And in that case, interior negative is 0.65 m naught, positive is 0.35, exterior negative is 0.65, 0.35, 0.35 m naught. negative, positive, negative, right? So that's how you distribute your static moment. Okay. There's so much in the table, but there's only one picture given, not even one picture available. If there were to be a small picture, then things life would have been pretty easy. Okay. So that's how you decide. And how do you, I mean, the next step is to take that moment on that has been distributed in, let's say, take the negative moment and further divide it or push it into a column strip and a beam middle strip. Okay. And that's, I think we'll reserve that for slightly deeper discussion. That completes direct design method. So we talked about flat, slab, flat plate, right? We talked about drop panel. We talked about shear cap, right? We talked about one-way shear. We talked about two-way shear and where those critical sections are and how to find that information in the code. We talked about how you can calculate the small VC value, which is the shear stress, shear strength value. We talked about how you calculate your alpha, that defines the character of your beam, ECB, IB by ECS, ECS, IS is slab, IB is moment of inertia of the beam. And we talked about how you can evaluate the minimum thicknesses um, for slabs, and we also talked about the influence area, about the shear. So we did cover decent ground today's class. All right, thank you very much.